today we'll be going over the results of our column buckling experiment that we performed for AERSP 305W. Those who performed it are Ethan, Connor, Jake, Joe, and Luke. And it was overseen by our TA Matanch. A column is a slender structural member designed to carry compressive axial loads compared to a beam that is designed to take bending loads instead. Buckling is a disproportionate increase in displacement for a small increase in load. The assumptions of column buckling theory are perfect boundary conditions. So for pin-pinned, it would be frictionless. For clamped, it would be solidly fixed and no motion in it whatsoever. And it is also purely compressive loading. Going over the formula to calculate the critical load, C is determined by the boundary conditions of the column itself. For pin-pinned, it's equal to 1, and for clamped, it's equal to 4. The Young's modulus is determined by what material the column itself is made out of. The moment area, or the moment area of inertia, is determined by the geometry of the cross-section of the column itself. And the length is the height of the beam, and it's the most important one because it's a square value. Column buckling is important for aerospace applications because the structures that we design must be strong enough to carry the loads of the mission itself. Structural elements must be also be rigid enough to remain in equilibrium so nothing moves when it's not supposed to. Aerospace structures are designed to have a very high strength to weight ratio because they must remain very light for how much they have to carry. And many thin-walled structures are used in this to be able to, such as D-tubes and the shells of spacecraft. And sandwiching designs such as these are used to reduce weight while increasing the area moment of inertia to increase the critical buckling load.
So our experimental procedure was designed to provide a perfectly axial load on the column, as well as measure the displacement of the column at the midpoint. So to do that, we had a horizontal beam on top, which was meant to be kept level in order to provide an axial load. To keep it perfectly level, we applied force at the load adjuster and the load wheel to keep it perfectly level. In addition to that, we needed the linear variable differential transducer to be set up at the midpoint of the column and also perpendicular to it. The linear variable differential transducer measured the raw displacement of the beam, which was then sent to LabVIEW and converted into net displacement by calibrating it previously. So to perform the experiment, we needed to first remove the weights, which are right here, as well as raise up the horizontal beam. So we would take out the column, put it in whenever we needed to, within the column mounts. So to replace the column, we would lower the horizontal beam and replace the weights. So in addition to the procedure, we had 6 different configurations of the column. The first one was pin-pinned. That was tested with the 18-inch, 21-inch, and 24-inch columns. That allowed for a moment about the ends of the beams, satisfying the boundary condition C equals 1 in the previous equation. The second configuration was the column, or the clamped column, which prevented a moment about the ends of the beams, giving us a boundary condition C equals 4.
2 methods for actually calculating the critical load value from the experiment when collected with the LabVIEW program are the asymptotic method and the imperfection method. The asymptotic method is the one shown up on the slideshow right now. As the 2 graphs show, we're graphing displacement on the X and load on the Y. As displacement increases, load is also increasing. However, once the load is reaching that critical value for each specimen, and starts leveling off as the displacement is getting greater and greater for very, very small incremental changes in the peak critical value. We only included two graphs for this slideshow just to have simplicity. On the other hand, we have the imperfection method for determining the critical load. This operates a little bit differently as we're graphing displacement over load on the x and displacement on the y-axis. Displacement over load is giving very, very small values as we're taking an already small number and dividing that by a large number of the load applied. So when graphed with displacement, it is giving us a linear graph, but the slope of that graph, which is supposed to represent the peak critical value, is very small. In fact, it's in decimal place. It's decimal place values. However, these graphs are very, very accurate, as a lot of them have an r-squared value of 1, and they don't have any b on their y equals mx plus b. They don't have any intercept whatsoever. So here's a tabular representation of these values that were actually calculated during the experiment. The two boundary conditions that we were using are pin-pin and clamp-clamp, as Connor and Ethan both mentioned, and different lengths for each of these scenarios, 18, 21, and 24 inches. The theoretical values for the critical buckling load are on the order of hundreds, whereas the load cell values, or the values that the load cell is actually measuring from the experimental cell, are 1/4 the value of the theoretical. This is because of the moment acting where the load cell is not actually measuring exactly where the specimen is, so you have to account for the difference in moment for that load. These last two columns represent the data found in the graphical methods for determining peak critical. The asymptotic method is pretty accurate when determining the peak critical value, as it's leveling off at that peak critical value. On the other hand, the experimental imperfection values, as mentioned earlier, are decimal values. We believe we had some sort of scaling error, but we couldn't quite figure out what went wrong and why these values are so small compared to the actual peak critical values. Now I'm going to turn it over to partner Joe, who's going to discuss more about the errors in calculation.
So we also thought it was important to include a graphical representation of our data for the asymptotic method. So this is really just to illustrate that a clamp-clamp column, as opposed to a pin-pin column, will have a much higher critical buckling load due to the stability associated with that boundary condition. We also wanted to show that with a longer column, you're going to have a much lower critical load for any boundary conditions. So what we're showing here is a graph of our slenderness ratio for the columns. So all this really illustrates is that as you decrease the area of your column and as you increase the length, it's going to cause you to have lower buckling loads because it really decreases the stability of the column. Also shown here is the critical stress versus the length of the columns, which again illustrates that as you have even just a longer column, it's going to decrease the buckling load of your column. So it's also important for us to go into the error of our experiment. So illustrated here are the asymptotic results. And as you can see, for all of them, actually except for the pin-pin 21-inch column, we had a -% error value, which all that really means is that every single time except for that one instance, we got an experimental value for the critical buckling load that was lower than the expected theoretical value. We also found that our mean and median values were in the order of 17% error, which is, considering our experimental setup and procedure, is really a fairly reasonable value, 4% error. We also found that without fail, the clamp-clamp method always had a higher percent error than for pin-pin columns, with our highest percent error actually being 32.28% for the clamp-clamp's 18-inch column, which really is just a result of the boundary conditions that the pin-pin is much easier for us to simulate than the clamp-clamp boundary condition, which will be discussed later when we go into sources of error. And you can also see here that our minimal percent error was for the pin-pin 24-inch column, which was only 8.29%, which, considering our average and everything, was actually, we were very happy about. So now Luke is going to go into our conclusion, making our recommendation for which method is better to actually determine the critical buckling load of columns, as well as what sources cause these errors throughout our experiment.
Alright, so before we get into the conclusion and we make our recommendation on which method was best for determining the critical load, we're going to talk about sources of error. So there are 3 primary sources of error that we concluded upon. One being the imperfect boundary condition. So our clamp boundary condition was our constant value equal to 4 as seen in the earlier slides. So should our clamp not have been perfectly tight, it may have allowed a small moment at the ends of our column, and therefore we can't conclude that our constant would be exactly equal to 4. The second source of error is not having a purely compressive load on our column. So this might have happened when our team of 2 that had to coordinate between the load wheel and the load adjuster. It was hard to make sure that our cross beam was completely perpendicular to our column, and therefore we may have had a compressive load that wasn't completely straight down. It may have been off to the side or diagonally, which would have caused our column to shear and not be completely compressed. And for that reason, we may have had different values, and our measurements and our experimental data may have been altered slightly and increase our percentage of error. And the last primary source of error is our linear variable differential transducer may not have been fully perpendicular to the column. So as said earlier by Connor, our LVDT had to be completely perpendicular to the column, and also was placed halfway in the middle of the column. That way we could measure the full deflection, the maximum deflection of the column. And so if the LVDT wasn't completely perpendicular to that column, it may have given us less, or even mostly less of the deflection than we would have expected that would have occurred at the midpoint of the column. And so those are the errors that we experienced. And then, so in conclusion, we as a group would recommend using the asymptotic method to determine the critical value of our load that would cause buckling of the column, for many reasons, including percentage of error and also just practicality. And as seen in our imperfection method, we had a scaling error. I'm not sure what caused that, but because of the error in that method, we're going to point towards our asymptotic method to actually determine the critical value. Thank you.